We're going to be taking a look at problems 7 and 8 from the Projectiles Launched at Angles review. In number 7, a football player punts the ball so that it will have a hang time or total time of flight of 4.5 seconds. So you can see we put that here in time in both the X and Y directions. And it's going to land 46 meters away, so that's my displacement in the X direction. If the ball leaves the player's foot 1.5 meters above the ground, you can see here in the picture that it leaves the player's foot a little higher than the ground. What must be the magnitude and direction of the ball's initial velocity? We're going to assume it's going to hit the ground some distance, 46 meters, away from the kick, which means the y displacement is negative 1.5. We do not know the initial velocity in the y direction because we don't know the velocity that comes off the guy's foot, and that's the question. We also don't know the angle, which we're going to need to find as well. Ultimately, when it comes to this problem, we're going to be solving this a little bit backwards compared to the way we normally solve angled projectile problems. Normally, at the beginning, we would solve for the velocity in the x and the velocity in the y using the hypotenuse v and the angle. In this problem, we're actually going to be solving for the velocity in the x and the velocity in the y using our x and y information in projectile motion equations, and then going backwards, and instead of solving for each leg of the triangle using the hypotenuse and angle, we're going to solve for the hypotenuse and angle using the legs of the triangle. So the first thing we can do is we can find the velocity in the x direction because we know how far it goes, 46 meters, and we know it takes 4.5 seconds to get there. Velocity is displacement divided by time when there's no acceleration. So the displacement, 46, divided by the time, 4.5 seconds, gives me an x velocity of 10.2 meters per second. So now we have the velocity in the x direction, or this leg of the triangle. In the y direction, we know the displacement, negative 1.5. We know the acceleration, negative 9.8, and a time of 4.5 seconds. We're going to be solving for v naught, so we're going to use the third equation, d equals v naught t plus 1/2 at squared. A little bit of algebra. To solve for v naught, I would subtract the 1/2 at squared term over to the left. That's why in the numerator here I have dy minus 1/2 at squared. And then to get rid of this t, I would divide that time, which is why time is here in the denominator. I can plug in my numbers. D is negative 1.5 meters, acceleration negative 9.8 meters per second squared, time 4.5 seconds, and again in the denominator, time 4.5 seconds. Plug all that into my calculator, and I find the initial velocity in the y direction is 21.7 meters. I now have the opposite side of my triangle. Since I have the adjacent side and the opposite side, I can do Pythagorean Theorem, which I did right here, where the hypotenuse equals the square root of both legs squared once they're added together. So Vx we solve for is 10.2 squared plus V naught in the y direction, 21.7 squared. Add them together and take the square root. And we find that the kick has to give the ball a velocity of 24 meters per second. Solving for the angle, the tangent is the opposite side over the adjacent side. So tangent of the angle equals the velocity in the y over velocity in the x. So to solve for the angle by itself, I would do the inverse tangent of Vy over Vx. So inverse tangent of 21.7 over 10.2. And when I plug that into my calculator, I get 64.8 degrees above the horizontal. So the kick's velocity is 24 meters per second at 64.8 degrees above the horizontal. Number 8, this might be the most challenging problem on this paper because there are a few answers that we have to go through to get this one. Number 8, for a women's volleyball, the top of the net is 2.24 meters above the floor, and the court measures 9 meters by 9 meters on each side of the net. Using a jump serve, a player strikes the ball at a point that is 3 meters above the floor and a horizontal distance of 8 meters from the net. If the initial velocity of the ball has an angle of 8 degrees above the horizontal, so you can see here's our 8 degrees, what minimum magnitude of velocity must the ball have to clear the net, and what maximum magnitude of velocity can it have so that it strikes the floor inside the back line on the other side of the net? So you can see we're actually a little bit higher than the net because the net was only 2.24 meters above the ground, but we're going to be hitting it 3 meters above the ground. So when we're trying to figure out the minimum velocity, we're basically saying, what velocity do we have to hit this ball with here so that it gets to this point right at the tippy top of the net? Meaning the displacement, since we were hitting it at 3, is going to be 0.76 meters down, or negative 0.76. The distance it has to cover to get to the net is 8 meters because you were 1 meter in from your jump serve. We know the angle is 8 degrees. So in the x direction, cosine of 8 degrees times the velocity that we're trying to solve for, the velocity we're going to hit the ball with, is our initial velocity in the x. And our initial velocity in the y is the opposite side. So the sine of 8 degrees times v. And the acceleration is negative 9.8 meters per second squared. We're going to have a simultaneous equation in this problem because we do not know the velocity and we do not know the time, but we're going to have two equations. In the x direction, d equals v times t. Rearrange for time, time equals d over v. In the y direction, d equals v naught t plus 1/2 at squared. This is going to be very similar to when we did problem number 6, when we had to take the time, even though we didn't have an exact number, and plug it in from the x direction into time in the y direction. So if you got number 6, then this one will hopefully make some sense for you. So taking our time in the x direction, which is the distance, 8, divided by the velocity, cosine of 8 times velocity, and plugging that in here in time and here for time squared, I'm going to end up with an equation, dy equals the v naught times t, 8 over cosine 8v, plus 1/2 a, 8 squared over cosine squared 8v squared. All right, so down here, if I take a look at my equation, this should be negative 0.76. Looks like the negative might have gotten missed in the copying of this document, but it is down here. Trust me, there is supposed to be a negative there. My apologies that it didn't show up in the scan. So negative 0.76 equals sine of 8v times 8 over cosine of 8v. That's what happens when we change v naught into sine of 8v. So sine of 8v, that's my v naught, times t, which is the 8 over cosine 8v, plus 1/2 acceleration, 8 squared over cosine squared 8v squared. This 8 squared over cosine 8v squared is the time in the x direction, and we have to square it because it's 1/2 at squared. We can simplify this a little bit. Sine of 8 over cosine of 8 becomes tangent of 8, and v over v cancels out, leaving me with just tangent of 8 times 8, plus 1/2 times negative 9.8 times 8 squared is negative 319.8. And I also divided that, cosine of squared 8, I divided the numerator here by that, so that way I didn't have to worry about that in my denominator anymore. So I have negative 319.8 divided by just v squared. We're going to simplify a little bit more. What we're going to do is we're going to subtract this tangent of 8 times 8 over to the left, and that's going to give me negative 1.88, so negative 0.76 minus tangent of 8 times 8 gives me negative 1.88, and that leaves just this fraction on the right side, negative 319.8 over v squared. A little bit more algebra. If I multiply v squared up over here to the left and then divide by negative 1.88, that's why I have negative 319 over negative 1.88. And to get rid of the squared with the v, I take the square root, and that gets me a minimum velocity of 13 meters per second. We're now going to repeat that process, except now we're going to have some slightly different numbers to find the maximum velocity so that it follows this slightly longer trajectory and would just get to the back corner of staying in bounds. In that case, my x distance would be 8 plus 9 for a total of 17. My initial velocity in the x is still going to be cosine of 8 times v. In the y direction, I'm 3 high, and it's going to hit the ground, so my displacement is negative 3. And my initial velocity in the y is still sine of 8 times whatever this new velocity has to be, and the acceleration is negative 9.8. But this problem is going to be done exactly the same way mathematically that the minimum velocity was done. I have my time in the x direction is d over t. D is just 17 now instead of like it was in the minimum where it was only 8. And in the y direction, the only change would be that my displacement is negative 3 instead of the negative 0.76. From there, though, the math is identical. D is now -3, but I still have sine of 8v and cosine of 8v in my denominator, and I just change that x distance from 8 to 17. And in this term, 1/2 times -9.8, the d is changed, again, from 8 to 17, but my denominator stays exactly the same. We're going to do the same math to simplify this. Sine over cosine becomes tangent. V over v just cancels out. So I now have just tangent of 8 times 17. Over here in this fraction, 1/2 times -9.8 times 17 squared divided by cosine squared 8 gives me -1444.1, and v squared is still hanging out here in the denominator. I subtract tangent of 8 times 17 over to the left side, so -3 minus tangent 8 times 17 gives me -5.4. Same algebra that we did over here to get v by itself. I would multiply v squared up to the left side and then divide by 5.4. So that's why I get the -1444.1 divided by -5.4. Take the square root to get rid of the squared here with v. And I find that I can't hit the ball any more than 16.4 meters per second, or it will go out of bounds.